to write order. Okay, that's what the initialization that we are going to do it. Okay, so 2, 9, 7, 6, 5, 8 in the order given. We just build a binary tree. Then we are going, and of course, while building a binary tree, we ensure that it is going to satisfy the shape requirement. Okay, it should be a complete binary tree. Okay, only the last leaf nodes may not be there. Okay, except that all other nodes should be there in the order. Okay, then we are going to verify only for the parental dominance, starting with the last parent. So in this case, in a given list, the first n by 2 with a flooring value represent the parental nodes in the heap. So in this case, the first 3 are the parental nodes. So that is 2, 9, 7 and 6, 5, 8 are the leaf nodes. So we are going to start with the last parent, that is called 7. So that we compare with its children. Of course, it has got only one children, and the parental value must always be greater than or equal to this children's. Okay. If not, then we are going to find the larger of the two children and we are going to exchange. In this, only one child, that is 8, so that we exchanged. Okay. So once we move 7 down, okay, down the tree, again this has to be checked with its children's further if there are. Otherwise, you can stop at this point and then you can check the parental dominance of the next parent, that is 7. So that we are verifying here. So 9 has got 2 children. Okay, and 9 is greater than or equal to both of its children. So it's satisfying the parental dominance. And then move on to the next parent, that is 2. So if you compare 2 against the two children's 9 and 8, parental dominance has not been satisfied. So you are going to find the larger of the two children, that is 9, and you will exchange 2 with 9. Okay, and then now 2 has moved down the tree, and now again the parental dominance has to be satisfied with its children in the current position. So 6, 5. So both of them are larger values compared to 2. We are going to find the larger of these two, that is 6. So it's going to be exchanged with 2. Now again 2 has moved one more level down the tree. Now earlier it was in the root. It has moved one level down in the previous iteration. Now one more position. Now it is in the leaf position. It has not got any children. So you are going to stop it. So that's how you are going to build the heap in the bottom of construction method. So in the similar line, we discussed the algorithmic approach. Okay, so that you are going to implement exactly by using a one-dimensional array, wherein which you are going to store the elements from the position 1 to n, and the 0th position is unused, or you can place with some larger values. Okay, so that we discussed in the last class. Now we'll see how you can construct a heap using the top-down approach. In the top-down approach, say you assume that right now you already constructed a heap. Suppose you would like to insert a new element or new key into the heap. First, you will attach that new key, that is after the last leaf node of the existing leaf. And then you have to shift that key element up to its appropriate place, because whenever you are always going to insert in the last position, when you insert in the last position, it may not be a heap, it may not satisfy all the properties of the heap. Then you have to reheapify that. Okay, so reheapifying procedure is same what you've done in case of the bottom-up approach. You have to compare that key with its parent to check whether the parental dominance has been satisfied. If not satisfied, you can find the larger of the two children and then you can exchange with its parent. What exactly you have done in the bottom of the same thing you have to do. And then once you move up, again you have to check with the next parent. Okay, so it's exactly the same procedure. We'll see an example. Now you assume that this is the 10th key element. Right now you added to an existing heap. Before adding that, I am ensuring that it is an heap. You can check the previous thing without a 10. It is satisfying both the shape property as well as the parental dominance. To take any parent, so 9 is the larger of its two children, 6 is a larger compared to both of its children, and 8 is a larger compared to 7. It's already an heap. Now you assume that you are adding a new element 10. As and when you added a new element 10, you have to check whether the 8 is greater than this step, because it's already an heap. You need not find the larger of the two children. You are just comparing 10 with its parent directly. Since 8 is smaller than 10, you can exchange. And when you exchange this again has to be compared with its immediate parent again. So this can be compared against 9. So dominance has not been satisfied. Again, you can exchange those two elements. So that's how the heap you are going to build in case of the top-down approach. Now we'll see one complete example of how you can build. Okay. So in this, you take the first element. So you take the first element and you will build a tree with only one element 2. And then you take the next element 9. You will add 9 as the left child of 2, because always you will add to the last position. When added, immediately you will check whether the parental dominance is going to satisfy or not. So in this case, it is not satisfying. So then you will check, you will compare the value of this 9 against 2. So parental dominance not satisfied, you are going to exchange that. That's what we have done in the next step. So here it is exchanged. So 9 becomes the root and 2 becomes a children of that or a leaf. Next, you will consider the next element 7. You will add it to the last position in this tree. So once you add it, again you are going to check for the parental dominance. Yes, it is going to satisfy the parental dominance after adding 7. Okay, now you will be adding the next element 6 to the, so this is 9, this is 2 and 7. Now you are adding 6. Once when you added 6, again you have to check whether the parental dominance is satisfied. In this case, compare against its immediate parent, it is not satisfying. So you are going to exchange 2 and 6. So 2 will come here and 6 and remaining elements will be there as it is. Okay. So now it is an heap. After exchanging, again you can check whether 9 is satisfying the parental dominance against its children. Yes, it is satisfying. Okay. So next you can add a next element. So it is 9, 6, 7 and 2, and the next element you are going to add 5. So after adding 5, again you can check whether the parental dominance is going to satisfy or not. You can compare that 5 against its parent value 6. Yes, it is satisfying. Okay, then only you have to consider the last element 8 is added as a child of a node 7 in the last position, because you cannot add as a children to 2 or 5 because it's going to be a complete tree. Okay, so it can be added only as a child of the node 7. So 8 is added here. After adding, immediately it has to be compared with its parent to check for the parental dominance. Since 8 is larger than 7, it has to be exchanged. So 8 will go to the parental position and 7 comes to the children position. And then again 8 has to be compared against 9. The parental dominance is satisfied, so no exchange. So in this way, you are going to construct the heap using the top-down approach. Okay, so it's a top-down approach. Now, so you can construct a heap either using a bottom-up approach or a top-down approach, but the bottom-up approach is the efficient one. So by using that, further we'll think how we can sort the elements using the heaps. Right now, we just discussed only how we can construct a heap. Okay. Now, before discussing the actual algorithm, we'll see first how we can delete an element from the heap. And usually we try to delete the largest element from the heap in order to perform the sorting operation. So that is why it is called as the maximum key deletion from a heap. See, if you look at this example, where will be the largest element always? Where will be the largest element always? It's a property of the heap. The largest element will always be in the root position. Okay, so that we would like to delete always. So if you look at this final heap, the largest element always at the top. Okay, now, and we wanted to delete that element. In order to delete that element, we are going to exchange the root key. Root key is always the largest element that we exchange with the last key of the heap. Which is the last key of the heap? In this case, it is 7. Okay, whatever it may be. We are going to exchange the root key with the last key of the heap. And then we are going to decrease the heap size by 1. So in that way, we are going to delete an element, the maximum element from the heap. So any is an array. Whenever you have an array of size n, we decrease it by n minus 1. A simple. Actually, we are not going to delete any element from the array. Simply, we are decreasing our array size, array heap size by 1. Okay. So you will swap the root key with the last key of the heap. Okay, and then we decrease its size by 1. Okay, but when you exchange the root key with the last key of the heap, okay, it may not be any heap. So you have to reheapify by applying the bottom-up heap construction procedure. Okay, because after exchanging the root key with the last key, it may not be heap. So you can look at this example. Suppose if I exchange these two elements, suppose if I make this as 7 and if this is 9, okay, and then if I delete this, okay, and is it going to be a heap? It is 7. It is not a heap because its children 8 is larger than 7. We have to reheapify. So that's another step to be taught. So you can look at this example here, an illustrative example. Okay, suppose if this is an heap and the largest element is at the root position 9. Okay, so that has to be deleted. And the last element in this heap is 1. So now we have exchanged 1 and 9. And then we deleted, means we decreased the heap size by 1. We deleted this element. And this is the resulting tree. And this is not a heap because after exchanging with 1 is at the root. But its parent, its children are larger. So we have to compare against its children and it has to. How do you reheapify? Whenever you wanted to construct or heap using a bottom-up approach, always you should start with the last parent. Which is the last parent here? This 8 is the last parent. We have to check for the parental dominance of this last parent first. Yes, it is satisfying. It is larger than its children. Then you have to check for the next parent, that is 1. So 1 is not larger than its parent. We have to find the larger of these two children, that is 8, and then it has to be exchanged. Okay, so 8, okay, and then it is 1. After exchanging, it becomes 8. Okay, so you will exchange 8 and 1 will come here. Once 1 move down the tree by 1 level, again the parental dominance of this 1 has to be checked. Okay, there are two children for the 2 and 5. Okay, again 5 is a larger and you have to exchange this with 5 and 1. So that you can see in the last. After final heapification, the result has been written. Okay, so you can apply the bottom-up approach to perform the reheapification. Okay, now you understood two things: how you can construct a heap. One is by using a top-down approach, another one is a bottom-up approach, and another one is you understood how you can delete the largest value from the heap and then you can reheapify. Okay, so now by using any one of the heap construction method, you assume that we are going to use the bottom-up heap construction. Okay, and then the maximum key deletion algorithm, how you can sort the elements. Okay? Heap sort is basically a two-stage algorithm. First, you have to construct a heap. Okay, maybe bottom-up approach we assume, and then we are going to apply the root deletion. Maximum key deletion is same